Long story short, the hydraulic actuator of choice you'll see over and over again in this series is the linear actuating hydraulic cylinder. So it'll be well worth our time to review the collection of cylinder schematics we introduced in the hydraulic cylinders lecture, available at the Big Bad Tech channel. Double-acting cylinders have a cap end port and a rod end port. The act of extending a double-acting cylinder routes pressurized flow to the cap end and dumps the rod end to tank. In contrast, the act of retracting a double-acting cylinder routes pressurized flow to the rod end and dumps the cap end to tank. Hence the origin of the term double-acting. Rod and cap end serve as both entry and exit points depending upon the action being performed. Single-acting cylinders, in contrast, have only one port and only actively perform one movement. Single-acting cylinders ordinarily rely on a spring or the weight of a lifted object to passively perform the opposite movement. This particular single-acting cylinder is hydraulically extended, spring retracted. The act of extending this type of single-acting cylinder requires pressurized flow to enter the cap end. When the cap end is drained to tank, the spring on the rod end passively retracts the cylinder. In contrast, this particular single-acting cylinder is spring extended, hydraulically retracted. The act of retracting this single-acting cylinder requires pressurized flow to enter the rod end. When the rod end is drained to tank, the spring on the cap end passively extends the cylinder. These types of single-acting cylinders are commonly utilized in fail-safe braking applications. Note, single-acting cylinders sometimes incorporate a drain port on the opposite end to keep this space from being obstructed by any accumulated fluid that happens to leak past the piston. The schematic symbol may or may not indicate this vent port. Single-acting cylinders don't always require a spring to passively perform the opposite action. Consider a ram, basically a single-acting cylinder with a rod so large it has no rod end functional area. To extend a ram, pressurized flow fills the cap end. To retract the ram, the cap end is slowly drained and the weight of the lifted object passively retracts the ram. We'll discuss flow control methods and counterbalance valves in later lectures that allow the controlled descent of a lifted object. To fill out the family tree of cylinders, you should be familiar with the following cousins, nephews, nieces, uncles, aunts, and distant relatives. A double rod cylinder obviously has two rods. Note there is no area nor volume differential between the two rod ends given identical diameter rods. Given these conditions, double rod cylinders can be used to ensure the same force and velocity in either direction. Tandem or duplex cylinders are kind of like back-to-back double-acting cylinders. Tandem cylinders are one permanently affixed entity, whereas duplex cylinders can be taken apart. A telescoping cylinder looks like an old-school pirate spyglass. Intensifiers are something new. They're not really actuators, since there's no rod that interacts with the outside world. They do kind of look and act like a double-acting cylinder, so that's why I put them in this group. Intensifiers are basically a double-acting cylinder such that a larger piston pushes on a smaller piston. Same force, smaller area. You should know what's happening. We'll examine intensifiers in later lectures. Additionally, you should be able to identify double-acting cylinders with cushion on retraction, cushion on extension, and cushion on extension and retraction. If a cushion includes a slanting arrow, this indicates that it's a variable cushion and the level of cushioning is adjustable. Moving on, let's review the schematic symbols of some basic valves, starting with a pressure relief valve. Pressure relief valves have a pressurized P port and a return port T. A dashed pilot line passage senses pressure on the P input, and a variable adjustment spring adjusts the pressure set point. Pressure relief valves limit maximum pressure by providing an alternate flow path to tank if an actuator stalls out at the limits of travel, a valve closes, or if flow is otherwise blocked. Pressure relief valves are customarily employed between the pump and the tank. Pressure relief valves are often identified on the schematic using the shorthand RV, PRV, or if it must be explicitly stated the relief valve is pilot operated, PORV. The pressure relief valve lecture, available at the Big Bad Tech channel, discusses the pressure relief valve in great detail. Directional control valves are valves that stop, start, or change direction of fluid flow. Directional control valves have a number of identifying characteristics. Positions are particular functions performed by a directional control valve. Ports or ways are the number of ins or outs to the directional control valve. The actuation method is the means the valve is shifted from position to position. Actuation methods include, but are not limited to, manual levers and electrical solenoids. Return springs either offset or center a directional control valve into a particular deactivated position. Modifiers like manual overrides and mechanical detents can change how a directional control valve asserts a particular position. Directional control valves are often referenced on a schematic using the shorthand DCV. If there is more than one directional control valve in a system, they're often assigned additional numeric identifiers, as in DCV1, DCV2, etc. The Directional Control Valve lecture, available at the Big Bad Tech channel, discusses directional control valves in great detail. If you are skilled in the contents of that lecture, as I expect you to be, by all means, pause the lecture and see if you can classify the following directional control valves. If you perform the classification correctly, you should have come up with the following titles. This particular directional control valve is a two-position, two-way, solenoid-actuated directional control valve that is spring offset into the normally closed position. Additionally, it features a manual override. This particular directional control valve is a two-position, three-way, manually actuated directional control valve that is spring offset into a position that dumps actuator port A to tank. This particular directional control valve is a two-position, four-way, double solenoid operated directional control valve that is detented. Such a valve could be used to control a double-acting cylinder that fully extends and retracts. Finally, this last directional control valve is a three-position, four-way, manually actuated directional control valve, spring-centered into a closed center position. When actuated by an operator into the straight-through position, P is routed to A and B is dumped to T. When actuated by an operator into the cross-connect position, P is routed to B and A is dumped to tank. Such a valve could be used to not only extend and retract a double-acting cylinder, but also lock the cylinder in position, even in mid-stroke, with a closed center position. In addition to closed center positions, you should be familiar with tandem, float, and open centers. A tandem center also locks the actuator in position, even in mid-stroke, similar to a closed center position. However, it does not block pump outflow. A float center, in contrast, does not lock the actuator in position, but rather allows it to float freely, hence the name. This allows the actuator to be repositioned by an outside force. Similar to a closed center, a float center blocks pump outflow. Finally, an open center does not lock the actuator in position, but rather allows it to float freely and be repositioned by an outside force. Similar to a tandem center, an open center routes pump outflow to tank, thus saving the pressure relief valve the necessity of being actuated. While we're on the subject of valves that influence the direction of fluid flow, recall that the check valve is a valve that allows free flow in one direction and blocks it in another. Schematically, the free flow direction pushes the ball off the seat. In contrast, the block flow direction pushes the ball onto the seat. Check valves are sometimes referenced on a schematic using the shorthand CV. If there is more than one check valve in a system, they are often assigned an additional numeric identifier, as in CV1, CV2, etc. Pilot to open check valves act just like an ordinary check valve in the absence of a pilot signal. In the absence of a pilot signal, a pilot to open check valve allows free flow in one direction and blocks it in another. In the presence of a pilot signal, a pilot to open check valve, as the name implies, opens and allows free flow in both directions. Pilot to open check valves are schematically identified by having a pilot line that forces the ball off the seat. Pilot to close check valves are just the opposite. Pilot to close check valves act just like ordinary check valves in the absence of a pilot signal. In the absence of a pilot signal, a pilot to close check valve allows free flow in one direction and blocks it in another. In the presence of a pilot signal, a pilot to close check valve, as the name implies, closes and blocks flow in both directions. Pilot to close check valves are schematically identified by having a pilot line that forces the ball to the seat. Finally, restriction or orifice type check valves allow unrestricted flow in one direction and allow regulated amount of restricted flow in the other. Restriction or orifice type check valves are therefore a form of flow control. Restriction or orifice type check valves are schematically identified by having a tiny hole drilled through the ball. The check valve lecture, available at the Big Bad Tech channel, discusses check valves, pilot operated check valves, and restriction type check valves in greater detail. Here's a new valve you might run across in a schematic. This is a manual shutoff valve and is used to isolate, turn off, or drain a system. Manual shutoff valves either use a globe, gate, or ball actuated by a handle. These valves are commonly used to lock out and tag out a system. A whole series of flow control valves exist that all use a common base schematic symbol, that of a narrowing of the passageway. Flow control valves are used to restrict, meter, or otherwise control flow rate to an actuator, thereby directly controlling actuator speed. Flow control valves are sometimes called needle valves for reasons I'll explain in the upcoming flow control valves lecture. Long story short, it's because there's a needle in the path of fluid. Pay attention because this schematic symbol is like a game of add-on at the playground. We'll start slow and steadily increase in complexity till someone breaks an arm. This is a fixed flow control valve. The size of the controlling orifice is non-adjustable. If we add a slanting arrow modifier, this is a variable flow control valve. The size of the controlling orifice is adjustable via an adjustable needle. This is a variable flow control valve with a check valve bypass. The check valve bypass forces the flow control valve to restrict flow in one direction and allows full flow in the opposite direction. You should be able to differentiate between restricted and full flow direction if someone tosses this schematic symbol on your desk. This is a pressure compensated variable flow control valve with check valve bypass. The vertical arrow modifier lets a technician know that flow rate will remain fixed regardless of applied load conditions, within reason. This is a pressure and temperature compensated variable flow control valve with a check valve bypass. The arrow and thermometer modifier lets a technician know that flow rate will remain fixed regardless of applied load conditions or the temperature of the applied fluid, within reason. In summary, the flow control valve family controls the speed of an actuator.